Hello, and welcome to Palisade Corporation's webcast, Monte Carlo Simulation, an underutilized Six Sigma tool, presented by Rick Haynes, Master Black Belt, Smarter Solutions Incorporated. My name is Jamison Romeo Hall, and I will be your host today, and I'll be available to help answer WebEx technical questions by chat. If you experience technical difficulties joining this WebEx session, please dial 1-866-229-3239. Alternately, you can email technical questions to support@webex.com. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you are part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by clicking on the question mark icon located on the floating toolbar in the bottom right side of your screen. I would also encourage you to visit our website and sign up for a free trial download of our software, including our lead product at risk, Monte Carlo Simulation for Six Sigma. We invite you to sit back and relax and enjoy today's presentation. I would now like to introduce your presenter, Rick Haynes. Rick, you have the controller.
Oh, hello. It doesn't look like I've got the controls yet.
Okay. Let's see what's going on. You have is ready. Hey, it's Murphy here.
Hello, everybody. This is always
just
part of technology, isn't it?
Yep. Almost ready.
Hello, I'm Rick Haynes. While he's fixing that up, I am a Master Black Belt. Been a Black Belt since Motorola time. I'm also a degreed statistician from the University of Texas. Don't know where you all are, but I am in Austin, Texas right now, and it's nice and warm here. I will be talking to you about using at risk within a Six Sigma world as soon as I can show you the slides.
Oh, sure. I'm still trying to make you the presenter on This is unusual. We're going to, isn't this unusual? I've got you. Oh, yeah, go to your Quick Start tab. Are you still there, Rick?
Yes, I am.
Oh, sure. Click on that Quick tab and see what happens. Now we're in business.
Oh, are we? Can you see my screen?
I see something. Click Share Your Desktop. Yep, now we're in business.
All right.
It's my new studio here with my new system.
I apologize for that, everybody.
Oh no, that was all Palisade.
You can see my screen?
Oh yeah, it looks great.
Great. We're going to start off here. What I'm going to start on and talk about is a little bit about simulation and Lean Six Sigma. Don't know how all you guys are involved with Lean Six Sigma. I have been in places that taught it as a black belt skill. It can be good, but it's not necessarily for everybody, but it's useful in almost all cases. I'm going to then walk through a manufacturing case study in our process that I would use to put together a simulation. So I'll give you the map. At the end, Jamison will email you and give you a copy of the simulation we'll run live, and you'll have a link if you want to get a more detailed PDF article or white paper on the topic that I'm talking on. A little bit more depth and discussion in it. First of all, why should you simulate in Lean Six Sigma? Well, there's sometimes it's your only option, and many of you may have found it. Generally, I find it's when there isn't any data, and you got to make some. A lot of times when you can't time the overall process because it takes way too long. I worked with one that had a 9-month cycle time, but we could measure each step. So you do that, measure the pieces, put them together in a simulation so you can estimate the whole process. The advantage is then you can test by adjusting the simulation rather than adjusting the process. The other times come up is when you have to test a new process before implementation. I find this is probably more common, especially if you're a transactional world. We think about Six Sigma for manufacturing, but in the transactional world, simulation is generally more beneficial, especially if you're looking at improvement that changes staffing or work schedules of the people, or it requires you to buy capital equipment or move it around and change transfer paths in the lean, if you're looking at the lean side. Those are very difficult to do to run a test to see if it's going to work. You almost have had to make the implementation and hope you're right. With these simulations, you can do things like that, prove that, I guess, demonstrate that the improvement will be gained before you actually commit resources. All right. In this webinar, I'll walk through an example that we're using it to predict future failure of a product and what the business would choose to do with that information. This was a spin-off of an existing project to go find a problem with an installed defect in a product that we rapidly found what was wrong, but the next question is, what do we do? And it was part of the improve and analyze part of the project, so we could give good guidance to the leadership. Do we replace them? Do we fix them? Or do we let it go and fix them as they break? All the work that I did was in Minitab, Excel, and at-risk add-in to Excel. I'm not going to show you the Minitab parts today, but I'll show you a couple places where you see we needed something other than Excel to do the math. All right? Assuming you all know about at-risk, it adds a lot of functionality to Excel to allow you to do a lot of random sampling to build math models. I find it's really great when you don't want to solve the equations yourself. It's easier to simulate them. Okay? Here's the context of this. Manufacturer had been producing a product for 3 years. It was warranted for 3 years after the installation. They wanted to look at 5 years. The installation generally occurred a year after manufacturing, so that made it tough. Soon, when most of them were built, they had about 1 million units in service. They started getting failures, and they had 104 by the time we started the project. What's tough, though, is they didn't expect any failures in 10 years based on other builds, so something was really wrong. The investigation found a non-compliant condition in the product. It was pretty clear. It was, there was a lot of installations, and they were rotated different ways. They were straight like the plan said, or they were rotated counterclockwise or clockwise from the original orientation, what it was expected. So they found the problem. They knew it would reduce the life, but there's 3 business decisions to make. Do I replace them all as they are, replace them as they break during the warranty period, or just modify them all in place so it eliminates the failures? What I'm not talking here is they did completely eliminate the cause from ever happening again, so that the question of future builds isn't in this project. They did find, though, that the labor to replace the product would be 10 times the cost of the product itself. So you can see they rapidly lost their benefit of this project, or of this product. Now here's a quick look at how I propose to do simulations and what I work through when I do them. See a little process map. What's part of your team? What's part of your sponsor or champion if you choose it? And how much you have to just go to your company. But you'll see a simple map there. The key points are you gather data, build the model, and then cycle through it in pieces until you can verify that it works. Once you've validated it, and we'll have a slide about that, then you do is you examine the simulation by modifying it and seeing how sensitive to its inputs, and you can predict future results. That's what this was about. So what were the constraints or the objectives when I examined them? Well, the goal of this simulation was to provide information to the leadership. Pretty clear. But they needed to balance the overall cost with the impact on customer loyalty. So this could not be just a straight dollar decision. Of course, you don't go for short-term gains to lose the big picture. To figure out the true failures, if you realize, or if you remember back there, we had 104 failures out of 1 million installations. You'd think that's nothing. That's way less than 1%, of course. But how do we know what's going to happen in the future? And they pulled cables, did an accelerated life test, which really you put it in the test chamber and ran it through its lifetime to see when it would fail. We really looked at only 3 factors with all the brainstorming and such that went down. There was the temperature of use, the magnitude of the non-compliance, and the orientation of the installation. I'm being a little soft about the specifics because I don't want this to drift into proprietary stuff, so we're just really talking about the simulation here. If you have some more detailed questions, please feel free to chat, put them into Jameson. I will answer the ones I can. Interesting thing on my side, to do this accelerated life test, we actually used the design of experiments to go generate the plan and estimate the impact of every factor. Our design ended up with 2 temperatures, 3 orientations, but the non-compliance was a covariate, it was a continuous number that we couldn't control in the test. It was just a number. So we put all 3 of those terms into a design of experiments using Minitab. The other downside of this is it didn't necessarily come up with a number because it had censored data, meaning some configurations never failed during the test period. Interestingly enough, since they cared about their customer, the total cost of this testing exceeded all the money and revenue they'd made from this one product. Now, testing was planned to run 2 times the normal life cycle, so we were hoping to run it equivalent of 10 lifetimes, or 10 years of life. Analysis would require a censored data analysis method. You can do it. If you want to do this in Minitab, I don't know if your users, you design it with the design of experiments tool, but you analyze it with the regression tool under life data, and it does work. All right. Now to gather data for the simulation. So we went out to the customer base and got an estimated number of cycles per year of the data. And we're going to do all of our work in cycles to failure. This data was compiled and tested and shown to be a Weibull distribution. Again, if that's skewed data with a long tail to the right. Then we looked at the temperature ranges of installation, which is common. We chose north and south and hot and cold. In our zones of installation, we had how much of the time was in hot cycles and how many were in cold. We were trying to simulate the environment that these products existed in. The next question came about is the orientation. We're going to predict the whole million item failures. We had to know how they were installed in orientation. So they surveyed a whole bunch of installations and came up with a ratio of there was 2 clockwise for every 5 that were normally put in and 3 that were counterclockwise. So as you can see, they got about 50% of them in the wrong orientation during installation. In the testing, we found that the magnitude of non-compliance, it was really a measurement of length. We found that it was not significant, so we could drop that. If it was non-compliant, it failed in these tests. We did find that orientation was very significant. The counterclockwise installations never failed at all during the test, and the counterclockwise installations had the highest failure rate. Interestingly enough, the last bullet is different from what you would normally find. Cold temperatures actually lasted longer than hot temperatures. Our expectation is that it stiffened things up so it didn't fail as much. We didn't get into the science of it. So here was the logic of the model. Because once you've got your information, the next step is how do you put it in a spreadsheet, which I will actually open up and show you how it ran. You can see there was 2 paths. One across the top was about the failure model. Choose the orientation and the region, since both those were found to be important. Estimate the model for that reliability. So we would have an output or an equation from the design of experiments. Then we would set the region to the right ratio of hot and cold cycles, and then calculate for that one piece the cycles to failure. So how many times it would cycle before it failed. In parallel, we had a usage rate. which could differ for every unit. So we would randomly select from our Weibull distribution how many cycles per year that installation would have. We multiplied by 10 to get the total cycles for a 10-year view. Now, if the total number of cycles in 10 years exceeded the calculated cycles to failure, we called it a fail. Right? So we changed continuous data into binomial data, pass-fail, and then we had at-risk collect all the cases reported in it. I'll show you its format. We also, as I show you, we collected the pass-fail data because that's what the customer cared about, but we also calculated also margins and such as that along the way. These were the actual at-risk commands we put in. You can see how we coded each of these issues. Use the log normal for the failure model because that's what it solves out of Minitab. A Weibull for the usage rate, and binomial, and then a discrete distribution for those ratios. All right. Our model then gave us, out of Minitab, these coefficients. So I'm trying to show you below how it turned into an equation so we could put it in Excel. The shape has got to do with the, I guess it's equivalent to the spread of the data. The scale sort of has to do with the mean time to between failures. Not exactly, but that's generally like a mean and the standard deviation. But with every region, we had different coefficients. All right. I'm sorry. For every position, we had different coefficients. The temperature was for the region. That was how it was. So it was affected with a continuous term. What the model did then is it would grab all the random numbers, calculate the values of cycles to failure and estimated cycles in 10 years, compare the two, decide if it had failed or not. All right. Here is the parameters that it used just to show you. For hot and cold cycles in each of the orientations. And then we took a ratio of those hot and cold distributions for how many times it actually cycled or how much stress was put on the unit before it failed. You see, they're close, but they're not quite the same. It was this complexity that forced us to go to something like at-risk rather than just doing a straight calculation. Okay. You may not understand all that yet, but when we see it on the Excel sheet, you'll probably understand it better. The next step is the hardest to do, and it was difficult in this model, and probably more difficult than any other I'd done, basically because I didn't have data. I had censored data. I only had 104 points out of, well, I said that's of 100,000, it should say 1 million. And I didn't know where the installation occurred, which zone, and I didn't know which orientation they were. All I knew was 104 failures and how long they had been installed. I'm sorry, how long they've since been manufactured. So I didn't even know how long it was till the cycling started. So what we did is we fit that data the best we could to a distribution using sensor data analysis, and then looked at the confidence intervals on the predicted percentiles at 5%, 50%, and 95%. Because I didn't have data to run t-tests or f-tests is what would normally be done. Generally, to validate a model, you should go back and test means and variances of actual and the simulation output. And probably the distribution should be the same too. That's generally how you go. This one was tougher, but we proved that within the percentiles of what it predicted and what actually was found in the reliability model came up close enough. Let's do a demonstration. Again, if you have questions, please chat them into Romeo, and he will interrupt us while we're doing this. All right. Can everybody see this? I think I can make it a little bit bigger. Let's try 120. Okay. What I have here, this is where the Weibull, where it grabs the number of cycles per year. This spreadsheet is one iteration of the model. If I go down, that's 10 times it. Here is the random draw for the configuration. You can see the ratio 352. The regions, north or south, with 60% of them would be in the south. When you get that, it tells you what % of the cycles total will be cold and hot. All right? And you can see the 40, 20, and 40, 60, and 2080. It then calculates for each draw, this is the number of cold cycles to failure and hot cycles to failure. It sums those up to the total number of cycles it took before it failed. So it's ratioing the total number of hot and cold. At the bottom, it'll tell me how many are operating at 3 years and how many are operating at 10 years. If that unit is, I mean. It can tell me the margin in cycles at 3 years, 10 years, and the estimated life at failure in years, how many years it would take to fail. These are the coefficients that it fills into all the equations. So let's try to run it. I will try to cover some stuff if you are interested in other things. These are the ones I am interested in. I'll run this 20,000 iterations right now. I know it's not a million, but you generally run a simulation until you get an indication of convergence. That means that the variation of the answers isn't changing much when it adds another data point. Let's run the simulation. Okay. You can see what it's doing is it's adding in its cycles. There's 100,000 or 10,000, 20,000. All right. Make this a little bigger. First thing you should look for is in this column that they all say open. It didn't. Look at that one, says 56. Not saying okay means that it didn't converge yet. This is the estimated life at failure. This is, I'll show you a little bit later why this one's so tough. So let's run it once more with more iterations, which is the next step you'd run. Being that this is truly random numbers, sometimes it converges earlier, sometimes it doesn't. You can watch them. I don't know how fast your screen updates depending on your connection, but I can watch them slowly fill up here. I still have the one left. So I'm at 20,000. There we go. I have convergence on all of them. Therefore, that is an indication that this answer is repeatable if I run the test over and over again. All right. Let's look at estimated cycles to failure. I want to show you, oh, it's not quite done yet. This is estimated cycles to failure. All right. What's interesting is you have to go look at this chart. I'm going to change it so you can see it better. I probably won't do all these, but we can look at this. I'm going to change the bins for the distribution to 0. The maximum will be 100. This usually catches me up on something here. Scaling will be 0. What I'm just doing is expanding the picture so we can see it. Let's see how it looks. Oh, I made a mistake. Make one more time at this. Okay, 0 to 100. Oh, I'm getting there. I even wrote notes down, and it worked when I did it. All right. Oh, I know why. I'm in the wrong chart. Oh, an estimated life in years. It makes a better picture. Okay. Look how funny this chart looks, because in years, there's always a couple that last forever. This is the one I need to change. There we go. That says the binnings for the histogram. I'm going to change the x-axis so that it matches what I want. forgot this one changes. There's my chart. Okay. So I can look at, this is what the actual failures were in years. If you can note it, most of them last an awful long time, 60 years. All right. So we're going to go then take this. All right. If I want to know how many are lasting at 3 years, I can put a 3 in here. I'll make it bigger so we can see it better again. 2.2% should have failed at 3 years. It's the expectation. So that's how I can use this chart. All right. One thing I also want to show is this data here, and one of the neat things about this process and why I had to use it, what I can do here is there's a button that will fit a distribution to it. We'll find that it doesn't fit any standard distribution because it is really a mixture of different products all into one picture. Why this is neat to the Six Sigma folks is generally at the business level, nothing is a nice distribution. They are all mixtures. In this case, it says an inverse Gauss distribution is the best. I don't care about that. Here's the first one we'd like to see is a log normal. All right. Chi-squared isn't normally used. I'll choose the Anderson-Darling, what most Six Sigma people use, and so the number is quite high. So it really doesn't fit that distribution. All right. But we find because of this mixture, I could not use standard statistics to show what it was. Now, what's my answer? I look at the bottom, still operating after 3 years. Make this bigger. 97.7% because I put the binomial check in there. How about at 10 years? 80%. So that's what you can get out of the simulation. All right. I'm going to go back to the presentation and finish up. What else can we collect? Well, the nice thing about a simulation, if you can use Excel, you could do a lot. We could actually pull the data set out and put it in a control chart to see if it's stable and predictable. Check margins at different points. As you saw, I put the 3% on the top of the chart. With the model, I can predict failure rates or total amount of failure at any point in the life, not just the one I calculate with Excel. So the power of being able to use simulations if you can describe it rather than having to directly calculate it. So what were the results? Given that we had a valid reliability model, we did check it against the warranty data. It was acceptable. The business decision was to repair them as they failed. They chose not to go out and do 100% like a recall, or to go, they found a fix that they could have modified each one so the failures would stop. It really stopped the failure mechanism in place. So they used these results as part of the DMAIC project to decide how the company should go forward. And again, it cost them money, but they balanced the customer needs and their business needs together. Well, I've been going just not quite a half hour, but it's half past. I don't know what questions you might have. I will say again that Jameson will be sending you the Excel file that I did the simulation with if you want to play with it. You can see the logic in it, you can see the equations. It's also interesting if you want to see how it randomly picks different parameters for the log normal distribution when it uses it. There's also a paper, a white paper written over this that tells a little more about the whole effort that will also be available. I believe Jameson is sending you a link so you can download it. Are there any questions?
Hey, thanks, Rick. Thank you very much. Let's see, I do have a couple questions. Couldn't you just do this in Minitab?
Well, no, but I guess that's not the real answer to that question. You can do some level of simple simulations in Minitab, but those who've used it may not realize it, but us old-timers were using punch cards with Minitab, and it still runs like it's punch cards. Information is always in columns and observations in rows. So if you wanted to run this type of simulation, you need 40,000 rows of data. It gets very clumsy, and it chokes most computers when they get that big. The other one is Minitab does not do this conditional type event well, because each random draw or each observation had to pick a random number for the orientation, a random number for the life cycle, multiply them all together, use the number for the orientation, then you pick the parameters for the distribution, and it actually generated a different random number for every point. Now, Minitab would have to use each of those multiple distributions to define a different column and then randomly sample out of it. It would be very clumsy. Matter of fact, I really tried it the first time and it didn't work. So Minitab is good at some things, but it isn't good for everything. All right?
Thank you. Why not just do a direct calculation of the life based on the failure distributions?
I am sure people can do that. I learned the math to do that in college, and closed form solutions are quite difficult. Now, there are PhDs that do that. This is really talking about a tool for us to solve problems and not having to be mathematicians or statisticians. At some level, I should be able to do that. I expect one of my instructors, my past, would be disappointed that I would say I can't do it. It's just too fraught with errors because people can't check you. The advantage of the simulation is I can look what the output looks like and make inferences based on that. It is quite a bit more powerful. All right?
Great. How many variables can it take with a regular P5 dual core?
Oh, you mean Minitab or? What?
Maybe our
Like
question.
Minitab, I believe is.
Oh, at risk, yes.
Oh, I'm not sure. On at risk, I have never found a limit on it. In the fact that it draws random numbers, does a calculation, and doesn't save all of it. So it does. You can get to a point that it will struggle, and I did it once, but it was because I had too many simulations and I used up my random access memory. It was not the CPU that drove the answer. The CPU drives how fast it goes, but no, it's memory, because it holds all of your simulation with all the random numbers and the calculations in random memory until you save it. So I've done 1 million simulations or 1 million iterations with this model, and it worked fine, and I don't have a high-powered computer. So I don't. So.
Did we help in designing this model? I don't know.
You, Palisade?
Yeah. No.
No, I've been an at-risk user for 7-8 years. It is relatively intuitive. The hard part is not the software. The hard part is understanding the sequence of putting the simulation together. Now, at risk, no. I called up these guys at Palisades and talked about doing this with them. No, this was not, I did not use a programmer at Palisades to do this. I'm going to answer a question that wasn't asked, Jameson, before we go on.
Sure.
What about how do you, because I forgot it. In writing a simulation, if you try to do it all at once, it'll take forever to troubleshoot it because you generally do not get it right the first time. It's almost like the same model you would do writing a software program. You build every block, and you look at it, and you test each sequence. If one's right, you go to the next sequence and add to it. It's too hard to troubleshoot it all at once. It also, are they still seeing my screen, Jameson?
Yes, we still have your screen there, yeah.
I wanted to show one thing, and I realized I didn't. I'm going to make it real short simulation. But one thing I didn't talk about, too, was you have to look at your inputs, and it does collect them for you. This should run really quick since I made it only 10,000. There you go. You should always look at your inputs and why it collects them to make sure they did what you thought. I can see here I got 3, 5, and 2. This is my usage rate. I can go look at the means and max and go see that they actually fit it. if I look at the distribution, it actually fits the Weibull to it that I created, and here's what it fit to it. All right. I can look at my distributions in hot and cold light, so you should always check your inputs as part of building your simulation. But no, I had no help from Palisades on this. All right.
Oh, is it possible to quantify the benefits and how much time, money you feel simulation saved in this project?
Well, I won't talk about their financials, but what the simulation did is measure their business risk. It really didn't, and whenever you do a Lean Six Sigma project dealing with a reduction in risk, it's very hard to estimate the dollar value. Many businesses have a common method to validate the value of reduced risk. These guys looked at keeping the customer as a future customer was way more important than the dollars it cost to do this. On other efforts of simulation, it's clear I'm using the simulation to validate the answer that I have come up with in other methods. So generally the simulation is to do a validation of it. It's not necessarily how the simulation itself that makes the money. Now, what follow on, how long did this one take me? This one probably took me about 4 hours to put together. And I probably spent another 3 or 4 hours adjusting it as I worked with the customer and tweaked it in when they give me different information. But if you're going to write one, you can probably do it by yourself, but just believe after you did it the first time, you're going to redo it again to make it smoother and simpler. All right? How are we coming on more questions?
Let's see. I've got for the improve area of DMAIC, would you use the at-risk optimizer to help redesign?
I have not used that, so I can't speak to that. I have used at-risk solely to fit distributions and to generate output data to simulate what I was measuring for my primary project metric, to do comparisons. And I enjoy this tool to do what if when I don't have to mess with the process. What if I have more people? What if I change the orientation? What if the temperatures change? It allows me to manipulate the business system electronically without having to do it in actual life. At some level, it's analogous to people designing computer chips now. The whole computer chip is designed on a computer, and they know it works before they make it. Most electronic equipment is all designed with simulators now. They put a battery in, they can estimate failure patterns and variation in voltages and run it all electronically, so before they ever create it, they know if it's going to work or not. And so I use it more like that. I am a traditionalist probably in the Lean Six Sigma world. I use the more traditional tools to go do the validations and the impact on the business.
Great. We have a few more questions, and I'll answer them. I can send our attendees in the right direction there in terms of looking for more models. Let me see if we have a couple more coming in, then let's see. I'll be sure and save all our...
and by the way, for those who...
go ahead. Go ahead.
I'll ask Jameson to put my email address on if anybody has any follow-up stuff they want to go ask me separate from whatever. Feel comfortable with contacting me.
Okay, good. And I'll put that in my follow-up that I send to everybody.
All right.
And also, one last question. Why do you feel Monte Carlo simulation is an underutilized tool in Six Sigma?
Well, I guess I got a couple answers for that. Generally, when we taught it as part of a black belt course, it extended it to a 5-week course. And part of it, we spent generally about 30 hours of training to use Monte Carlo simulations at risk in some other different ways. There's some things you can do in Minicab and other tools. Probably the hardest part is it takes a more logical, programmatic, or programmer side to think through the process. When we taught it to black belts, I was with Bechtel at the time, we required everybody to do a simulation as part of their training project. About a third of them never could do much other than simulate something simple, and probably 1 in 10 benefited their project from it. And we sat back about 2 years in and said, why? And we found it was more the type of person than it was the project. Projects that are in manufacturing that have a lot of rapid number generation, simulation's not as big of an issue because they can actually generate a lot of data. It was more found in the transactional processes that dealt with people and behavior changes made simulations more beneficial. So underutilized, I think it's because most people don't understand it and don't teach it. It'll be my second answer to the question. I don't know of an ongoing black belt or Lean Six Sigma practitioner, consultant or otherwise, that teaches as part of their course. And I think a lot of it's because a lot of our current instructor base out there's never done a simulation before. These tools might be used in your company. If you like it, chances are a lot of the financial organizations use Monte Carlo generation to do risk assessments on bids and contracts and such. But it's because no one did it. This was not used when Motorola started Six Sigma. It wasn't used much with GE when they made the next generation. It's really come about since then as they spread out in other genre and people have used simulations as part of their other job. They brought it in. So I avoided the answer because I don't really know. I just have my opinion. Is that all right?
That's fantastic. So everybody, I am going to email this model out and some more information about some more. In fact, I might overload everybody with more information, but that's kind of part of my job. And I hope everybody enjoyed this. I certainly did. And I want to thank Rick Haynes again. And if you have any questions, you have my contact info. You can just beam more questions to me, and I'll keep you in contact with Rick too. And I want to thank everybody for coming.
All right. Thank you very much.
Hey, thanks, Rick.
Bye.
Really appreciate it. And thank you, everybody.